Okay, so let's start. Last lecture we were looking at mobility, and this was the slide that we had, and where we said that the simple model for mobility that we have is based on a probability of scattering given by dt by tau, where tau is the scattering lifetime. And then we said that there are different mechanisms of scattering. Two of the most important ones for us are the lattice of phonon scattering, which we will see in more detail today. The probability of a electron getting scattered due to this mechanism is dt by tau L, whereas this is the scattering lifetime associated with lattice scattering. Similarly, the probability that my electron gets scattered due to an impurity, that's associated with a different time constant, which is tau I here. And then we said probabilities, these are independent processes here. So the total probability that my electron gets scattered is probability due to this mechanism, plus probability due to this mechanism, plus the other ones that may be there. And that allows us to write an effective lifetime, 1 over tau effective equal to 1 over tau L plus 1 over tau I, and plus whatever other mechanism is there. So lifetimes then, they add up in an inverse manner here, because probabilities add up, and probabilities are inversely proportional to lifetimes, so lifetimes add up in an inverse manner here. And since mobility is directly proportional to lifetime here, so mobility, one can define a mobility due to only lattice scattering or a mobility due to impurity scattering. And therefore, the effective mobility, net mobility, will be 1 over mu equal to mobility due to individual components here. All right, so that allows us to separately study a mobility due to phonon scattering, a mobility due to impurity scattering, and so on and so forth here. And this rule here for adding mobilities is what is known by this Mathiassen's rule here. All right, so this is what we had done in the last lecture. Okay, so a little bit more on impurity scattering, and then a lot more on phonon scattering here. All right, impurity scattering we had seen here. Just to remind you, what I want to illustrate again with this simple animation is that impurity ionized scattering would vary with temperature, would vary with electron velocity. Okay, for example, if I have an electron, if it's moving slowly, is going to be under the influence of the impurity atom a lot more, and it will get scattered a lot more. On the other hand, if I have an electron here which is moving very fast, and you can see it's not going to scatter that much. Okay, so the simple animation is what it is telling us is mobility will, the dependence of mobility, there will be a dependence of mobility on temperature. And as I reduce the temperature, note that as I reduce the temperature, you know that the thermal velocity of an electron reduces. So as I reduce the temperature, my electron will suffer from impurity scattering a lot more. While as I increase the temperature, my electron will suffer from impurity scattering a lot less here. And therefore, we have a dependence of mobility on temperature. Mobility due to impurity scattering should increase with temperature. And I'm not going to justify this factor 3 by 2, but we can understand that it would be proportional to temperature, and it would also be inversely proportional to number of impurity atoms which are there. The higher the impurity atoms, the more the scattering. So as a very simple rule, one can say impurity scattering would depend at least on these two factors here. Okay. All right. What people have done is people have measured mobility. Towards the end of the lecture, if we have time, we'll look at how mobility is measured. So they've measured mobility as a function of, for example, number of donor atoms that you've added. Okay. So as you add more and more donor atoms, note that each donor atom, we said, will be ionized. And so we have an ionized impurity, and that will contribute to scattering. Right? That will allow the mobility to decrease here. And so people have empirically measured mobility as a function of number of donors that you add, and then they have fitted expressions to it. And one of the popular expression is of this kind here, that mobility goes with the number of ionized impurity atoms, which is Nd, in this particular manner here. So there is a constant term, 55.24 here, and there is a term here. So the idea is that, you know, this is the simple model that we have, but then mobility does not, as you can expect, that if I go to very low impurity ion concentration, it's not the impurity which is affecting the scattering. It's not the impurity which is determining. Go back and look at this expression here. If we look at this one, which term will affect the mobility? The one which is smaller. So when I go to low impurity concentrations, what happens is this term becomes large, and therefore it's no longer affecting mobility here. Is then lattice scattering takes over here. Okay, so at lower impurity concentrations, I don't expect this to play a role, and that's why you see this when I have low, I have a factor of 1 here, so that when ND becomes very, very small, it's not that the mobility keeps on rising. Okay, so look at this one here. Then mobility has, if the donor concentration is small, mobility is independent, even though ionized impurity atoms are there, but they don't have that much impact. Mobility is being determined by lattice scattering or phonon scattering here. Then as the impurity concentration starts increasing, then that particular scattering mechanism becomes important and mobility starts to fall. Mobility starts to fall here. And it keeps on falling. And then at very high impurity concentrations also you start seeing some leveling here. It starts to, so impurity ions are not influencing as much as they were influencing here. And the simple reason for this is screening. When you have a lot of impurity or donor atoms here, you have a lot of electrons in your system here. So the electrons that are present, they sort of screen the effect of the charge due to electrons sort of screens the effect of the ionized impurity atom here, and that screening effect start to become more important, and that's why it starts to level off here. So here it is constant because the impurity ion concentration is small, impurity scattering is not that significant, then it becomes significant, starts to drop, and here, and then it starts leveling off because of screening effects here. So that's the dependence on impurity. You can see here the effect of impurity, ionized impurity scattering here. Note that below 10 to the power 15 or about 10 to the power 16, 10 to the power 15 or 10 to the power 16, there's not much effect of impurity scattering here. Okay. Now a similar kind of an expression will hold for acceptor atoms also. So I can add here an acceptor, and similar dependence will be there for the ionized acceptor atom scattering also. And if you have both donors and acceptors, then what you can do is you can have here ND plus Na here. So if there is a particular semiconductor layer where you have donors as well as acceptors, just add the total impurity concentration here. Okay. All right. Temperature dependence of mobility. Well, the impurity ionized scattering that we have, as we said, mobility here increases with temperature. The lattice scattering, as you may expect, should decrease with temperature, because the higher the temperature that I have, the more the vibrations in my lattice, and therefore it should reduce mobility. Again, as I said, we are not looking at these exponents here 3/2. They come from more detailed treatment, but we expect that the mobility due to lattice scattering should decrease with temperature, and mobility due to ionized impurity scattering, we have just seen, should increase with temperature. And therefore, and note that mobility adds up in this inverse manner here. So therefore, what one would expect is, suppose I were to plot log mu, deliberately log mu, because if I take log here, then log mu versus temperature will become a straight line. Okay, so for that, okay. So log mu versus temperature. So this part says mobility should increase with temperature. This part here. Well, of course, it's not going to keep on increasing, because note that as it keeps on increasing, the importance of mu I will become less, and then mu L will take over. While mu L tells you that mobility should decrease with temperature here. So what you would expect is that the overall dependence of mobility on temperature would be at very low temperatures. At very low temperatures, it is this term which dominates, and you find mobility increases with temperature. Then at higher temperatures, you find the mobility is decreasing here, and somewhere in between, then you would expect a smooth transition from one to the other here. All right, so that's the kind of a dependence of mobility on temperature that you expect here. Starts to increases, sort of saturates here, and then starts to decrease here. Okay, and these are different mechanisms that are affecting mobility. Impurity scattering here dominant, lattice scattering dominant here. Now, typically at room temperature, for silicon, you are somewhere in this particular region here, in this part here. Okay, So mobility at room temperature for silicon, you would find is under typical conditions, you would find that it's decreasing with temperature. So if you are at room temperature and then you go to 50 degrees Celsius or 70 or 80 or whatever, you find mobility will reduce with temperature. Okay, so that's the both I've written for electrons. For holes also it is about minus 2.2 or so. Okay, so very similar. The hole mobility also reduces. So room temperature is somewhere here. Okay, so you are in this particular regime. You're not here. All right. This one shows a more a quantitative data on mobility. You can see that if you look at 10 to the power 14 doping, 10 to the power 14 doping. So this is the general behavior that you expect here, right? But 10 to the power 14 doping, why is it that we don't see this? Because impurity scattering, number of impurity ions is very small, right? And this is the one which gives rise to this particular part here. So you don't see this part at all. What you see is mobility keeps on increasing as you lower the temperature. You're not seeing this part here. Then as you go to 10 to the power 16, you can see a slight curvature here. And then this starts building, 10 to the power 17. We know that below about 10 to the power 16 or so, ionized impurity scattering is not significant. Okay, so we don't expect much, we don't expect this particular part here. But then you begin to see 10 to the power 18, you can see here, goes here, 10 power 19, you can see very clearly what the effects are. Okay, so that's the general behavior of mobility as a function of temperature here being determined by two different mechanisms here, ionized impurity scattering and the lattice scattering. All right, this is the example that we had seen earlier. In the last lecture, we had seen mobility calculations for silicon, and we had seen the effective lifetimes being 0.22 picoseconds here. So the important point here was the mobility of holes is less as compared to electrons for two reasons. One is its mass is higher, and the other reason is it scatters more here. Scatters more as compared to electron. And note that the scattering lifetimes are in 10 to the power minus 12. A few tenths of a picosecond here. Now, let's look at this is a picture of mobility in different semiconductors. All right, somebody likes to call it this hour. Every lecture, I think I get a call at this. Okay, so if I look at the semiconductor, different semiconductors that you see here, and look at the mobility values that we have. We have a range of mobility values here. Silicon is what? See 1500, some people quote 1400 also here. So silicon, this is the mobility values in intrinsic silicon. Okay, intrinsic silicon here. Germanium is another semiconductor, 3900 and 1900 here, holes here. Gallium arsenide is an important semiconductor, 8500 for electrons, 400 for holes. Look at this one here, indium antimonide, indium arsenide, 33,000, very high electron mobility. Hole mobility, on the other hand, is still 460 here. Holes are. So in all these semiconductors, you find electrons are a lot more mobile than the holes here. So if you take this particular example, indium arsenide, if I look at indium arsenide, we just saw for silicon, what was the effective mass of electron? Do you remember? 0.26 here, right? Go back and say silicon 0.26 here, and effective mass for holes was 0.36 here. So now you look at this particular term here, indium arsenide, effective mass here is 0.023, one order less. One order less, you can immediately see one order less means simply on the basis of effective mass here, it would have gone to 15,000. Okay, and plus as the masses changes, the scattering and all that also change. The energy band diagram changes and scattering also changes. So a lot of it can be explained on the basis of the effective mass. And similarly, note that the effective mass of the hole is still comparable, 0.41, and the effective mass for electron was, effective mass for hole was 0.36. So that's why you see the mobilities are for electrons and for holes are comparable to, silicon, but the mobility of electron is much higher here because of much lower effective mass here. Okay. Plus, although the mobilities are very high, note that the energy gap is only 0.36. Will that bother you? A low energy gap. From our discussion in the previous lecture, low energy gap will result in what? Low energy gap. What is the immediate thing that comes in your mind? I have low EG. What equation gives you what relationships exist with EG? Carrier density, does it depend on EG? Ni, does Ni depend on EG? Intrinsic carrier concentration. So intrinsic carrier concentration would be how high here? For silicon, how much was it? 10 to the power 10, right? For a band gap of 1.12 eV. Now imagine this is 0.36 eV. And what is the dependence of intrinsic carrier concentration on band gap? Minus Eg by 2 kT. So you can imagine what will happen to the intrinsic carrier concentration, right? So it will become very high. But then how does it affect you? Okay, let it be high. How does it bother you? All right, so remember this diagram here? Okay, maybe one can, here. See this? Where is this occurring? The semiconductor is becoming intrinsic, right? And at what temperature does it happen? We said in silicon, this is 10 to the power 16, and this was happening at very high temperature. But then I give you another example. Suppose I take a semiconductor 0.7 eV, and I put 10 to the power 15, this temperature goes at 100 degrees Celsius. Now this is only for 0.7. Now suppose I have 0.35. Where will this temperature go? So you're seeing now, I've put 10 to the power 15 doping, but my semiconductor is behaving as intrinsic, right? So that's one problem that you see here, okay? So the temperature begins to affect your device a lot because the energy gap is so small, so thermally generated carriers are so large, okay? So that begins to bother you. The other thing that will bother you is, I just want to illustrate, you remember donor neutralization? What did we say that for a donor atom to be ionized, what is it that you require? You require for a donor atom to be ionized, if we go back and look at this one here, our discussion, you require that this donor level should be close to EC. That's one thing. What else do you require? You remember that this relationship has to be obeyed. So if you add 10 to the power 16, let's say donor atoms, or 10 to the power 17 donor atoms, if you want them to be ionized, you must obey this equation, right? To obey this equation, you would like this term on the right to be as large as possible. Okay, so that one way of doing it is, let's say ED is close to EC. But another very important factor is NC. How large is NC? Effective density of states. And what does NC depend on? What does NC depend on? Well, let's go back and see. What does NC? Where do we have NC? Somewhere do we have NC expression? I think somewhere else, somewhere I had an expression for NC. It was here. Yes. Can you, here. Look at this. Expression for NC. What does NC depend on? Temperature and all that, but can you see where does the nature of a semiconductor come into play? NC is different for different semiconductors. Where does it come into picture? Effective mass. So now think about it. You are getting in indium arsenide very high mobility because of effective mass being low. Effective mass becomes low, what will happen to NC? NC will become low. And if NC becomes low, what are the implications for donor ionization? You know, the right-hand side of that expression is becoming low, so it becomes difficult for donors to get ionized. So, you are getting that high mobility due to small effective mass, but you're seeing that it's coming at a price. It's coming at a price because Ni is very high. Ni becomes very high, so it's very sensitive to temperature. Density of states begins to fall here, so I can't dope it enough. Okay, because if I dope it enough, now the donors are not ionized. So you get into all those issues here, which are related to the effective mass here, okay? So that's why, you may be wondering, I have a semiconductor which has such a high mobility. Why is nobody using indium arsenide? It's not that people are not trying to use, but why is indium arsenide not seen everywhere? So one of the reasons is, as we just said, the the fact that it has a very low band gap. If it had a band gap of 1.12 and very high mobility, then of course it would have been very attractive. Okay. So a large part of difference in the mobilities that you see here, I just wanted to illustrate, is coming about because of effective mass. Effective mass is being quite different here. All right, so let's come to our discussion related to lattice scattering here. And as I've mentioned, well, so let's start our discussion with a very simple model about, let's say you have a spring and you have a mass attached to a spring and this is attached to a wall. And all of you know if I stretch this particular spring here, it's going to vibrate, right? It's going to vibrate. And the simple equation for modeling this is the force, and the force is related to minus kx here, Hooke's law, and therefore is going to vibrate. And you know that vibrations xt, the deviation from its equilibrium position will be a sine omega t with some phase, and it will vibrate at omega equal to square root k by m, right? So that's something that you know from your school physics here. Now, so the picture, now lattice, as you know, the atoms are there in regularly arranged. So in a lattice, we can imagine a very simple one-dimensional lattice as atoms that are here, and the bonds that in between that are there here, you can imagine it like a spring. Okay, you can stretch the bonds and you can, so we can very simply model it in this particular manner. Okay, now when you do that, now remember this was one single spring and a ball attached here. Now so the vibration, the motion of this one now is coupled to the motion of this one, is coupled to the motion of this one. So they're all coupled together. So now I'll not go into the details of the maths. I'm not going to work this out. Okay. These are not difficult, but more time consuming here. So if I focus on, let's say this particular, the atom here, the motion of this particular atom or the deviation xn from its equilibrium position, one can imagine that the forces that are acting upon it will be one coming from this spring, whether it's compressed or elongated, and the other coming from this spring here, right? And so therefore you would expect xn minus 1 would tell you how much this is elongated or compressed, and xn plus 1 minus xn will tell you how much is this elongated and compressed. So you get an equation of this kind here. Force 2kxn plus kxn minus 1 plus xn plus 1 and xn minus 1. So now, because the motions are all coupled together. So now if I want to solve, one can show that you can take a solution of this kind here. You can take a solution as xt, which is let's say xn, the motion of, let's say, the nth atom here. You can write it as some constant, exponent minus I omega t, exponent I q na. N, of course, refers to the nth atom. A is the lattice constant here. And Q is if this is omega, then Q is like a wave vector. It's like a lambda. I've not used K. Normally people may use K here, but since K we are using for an electron, wave vector for an electron, so I've used Q here to denote wave vector here. So you can substitute here and you can see that it satisfies this particular equation. Okay. So now, here it was simply vibrating. Now what we have is the vibration is like a wave here. It's like a wave here. You can see that this is the equation of a plane wave here. So now the solutions are, I'll get different values of solution, and one can show that my solutions must obey this relationship here. Omega equal to square root 2k by m. K by, is the spring constant now. K is not a wave vector. So omega 2k by m, 1 minus cos qa. So what is this telling me? So let's arrange this here and let's plot it here. So what it is saying is, I have the following, that when you have a string and then it can vibrate in different modes. So these are nothing but different modes of vibration of this 1D lattice here. One particular value of omega will be associated with one particular value of q, because omega and q are related together, and that's one mode of vibration. Another value of omega will give you another value of q, that's another mode of vibration. So I have my whole lattice can now vibrate in these different modes of vibration here. And you can plot this out and you can see this modes of vibration here. It's a simple plot of sine here. So sine goes here. And after that, q beyond pi by a is a periodic function here. So you don't need to plot. Okay. So what is this picture telling us? That a 1D lattice can now vibrate in a series of modes. I can have a mode with a particular omega, a particular omega here associated with a particular Q. So what is happening is, if I look at this particular mode here, each one of these atoms, as you know, is vibrating with what frequency? All of them are vibrating with the same frequency, omega. Frequency is the same, right? Omega, each one of them is vibrating with the frequency omega. What does Q denote? That the phase of this particular one differs from the phase of this particular one and differs from the phase of this particular one. How does it differ? It is this phase factor here. Each one of them is vibrating with the same frequency, but the phases are the different here. X here, this one will be a little bit out of phase with this one will be a little bit out of phase with this one, and this phase part is described by this wave vector here, Q. And the phase is changing as you go along the X direction here. That's why it depends on NA here. And so there are all these possible modes of vibration here. Okay, it's not that, if I have n number of atoms, what you need to do is divide this whole thing. It will be discrete. Divide this whole thing in terms in n equal parts here, and you will get n modes of vibration. If you have an infinite lattice, then of course this becomes a continuous curve here. So my 1D lattice then can vibrate in these different modes. That's a classical picture of what is happening in a lattice. We have not used any quantum mechanics. We've just done a simple Newton's law here, and simply looked at what these solutions are. Okay. All of you remember this relationship for a sound wave, or any wave, that velocity is equal to lambda into f, right? Lambda I can write as lambda by 2 pi multiplied by 2 pi f. So 2 pi f is omega, and 2 pi by lambda, I'm calling it the wave vector, so we call it q. So what is the slope here that it denotes? See, we are talking about vibration. So what does the slope denote? Is the velocity. So vibration is what? So this is the velocity of sound wave in my lattice. That's what it is. Omega versus k, if I take the slope here, is telling me the velocity of sound wave in my lattice here. So that's what these vibrations are. Okay. So I have all these vibrations now. These are the different modes that you can imagine here. I have a mode of vibration which is like this. I have another mode. So this has a very large lambda or very large q. Very large lambda. This one has a smaller lambda, and then you can have an even smaller lambda here. So you have all these different modes which are there here. Okay, different modes of vibration. And so now let's bring in and remember, any vibrational state that you have of your lattice can be expressed as sum of modes here. That's Fourier series. Once you get these solutions here, these individual modes that are there, these are the different type of modes that are there here. Now your lattice is not going to be, you can imagine your lattice is not going to be either in this mode or in this mode. It's not going to be in such nice orderly manner that all the atoms are displaced in this nice manner here. But no matter what the state of the lattice is, it can be expressed as a sum of these modes here. So you can always, no matter what the vibrational state of the lattice is, you can always decompose it into a sum of either this or this or this or this. Okay? So any vibrational state can be decomposed into the modes of vibration that we have here. Okay, so that's the other point here. So any state, I can express it as a sum of here. All right. Now, in a particular state of lattice, what would happen is some modes meaning particular omega and q, some modes may be more excited, right? Which means strength is large. Some may be less excited, right? The strength is less, and some combination of A denotes the strength of each vibrational mode here. So A will vary depending on what the state is of the lattice here. A would vary depending on which modes are excited, which modes are not excited. Now, where quantum mechanics comes into picture is as follows. Quantum mechanics tells us the following, that energy in a mode. Yeah, one of the features that quantum mechanics describes is energies are always quantized. So what it says is the energy in any particular mode is quantized. It's of this form. h bar omega half plus n. N could be 0, 1, 2, 3, 4, and so on and so forth. So you take one particular mode. One particular mode means what? Take one particular value of omega, and associated with it would be a q. That's the mode. And that mode can be excited more or less depending on this amplitude aq. Now what it is saying is that the energy associated in that particular mode is quantized. The energy can only change in packets of h bar omega. So you can take a mode, and if you want to excite that particular mode more, what do? You add a packet of energy. How much? H bar omega. You want to excite that particular mode, you have to add one more packet of energy of h bar omega. And like that, if you keep on adding these packets of energy, h bar omega packets of energy, the mode will get more and more excited. So how excited is that particular mode depends on how many packets of this h bar omega you've added. Okay. All right. So recall what the picture is then. If I have a lattice like this, in the lattice, I can say that the lattice can vibrate in these different modes that are there. This is omega versus q diagram, which tells us all the different modes that are present. Any vibrational state of the lattice can be decomposed into these normal modes. And then we are saying that energy in a mode quantum mechanically is quantized. Energy in a mode can increase or decrease in packets. It can't, this classical expression says A can be anything. Starting from 0 to very large value, it can vary continuously. But quantum mechanics tells us that no, the energy here cannot change continuously, but energy can only change in packets. And energy in a mode can increase or decrease in packets of h bar omega. And you can imagine these packets of energy are what we call as phonons. Similar kind of a discussion, I'm sure you have seen that in light, in electromagnetic wave, the energy can increase or decrease in packets of energy called h bar omega. And we call those particles as photons. And the same analogy is there. We call these particles as phonons here. Okay, we call these particles as, so think of phonons now as something like a quasi-particle. As a quasi-particle, how much is this energy? H bar omega. It's not a real particle, but what is this sort of momentum? Momentum would be something which behaves like a momentum is h bar q. Remember for a photon, what was the energy? H bar omega. What is the momentum? You remember h bar k or hc by lambda, right? So h bar k. So it's the same thing which is happening here. Phonon energy is h bar omega, and its momentum is this h bar q. So what is the picture that we have of my lattice now? So I'm not going to think of my lattice with these vibrations and all of that. What I can think of is, in my lattice, what do I have? All these vibrations, I have phonons. And what kind of phonons? Phonons would be of various omegas. I would have a phonon with this omega, another phonon with this omega, another here, all kinds of phonons that are there here. Okay, and associated with each phonon, there's a well-defined energy h bar omega, and there's a well-defined, if you would like, something like a momentum, which is h bar q. So these are now, you can think of these are like quasi-particles which are there in my lattice, right? So I don't need to think about lattice vibrations anymore. What I need to think about is phonons. That they're all over in my lattice. There are phonons of different omegas, different q's, and how do I talk about how many phonons are there in a particular mode? Well, this is described by Bose-Einstein statistics. Like Fermi-Dirac statistics was for electrons, their occupation probability. Here, these are, if you want to read more, these phonons are like bosons, and they obey Bose-Einstein statistics, which tells us, let's say I look at a particular state Q, which is associated with particular omega here. How many phonons are there in a particular state is described by this function here. 1 by exponent h bar omega by kt. This is omega as a function of q, not multiplied by q, but omega as a function of q. H bar omega by kt minus 1 here. So you can see here, if I lower the temperature, what happens to the exponential? It increases. Number of phonons decrease. If I increase the temperature, the number of phonons will increase. Where would more phonons be? Will I have more phonons here or here? Obviously, at lower h bar omega, I will have more phonons here. So I will have a lot more phonons maybe at lower, and I'll lesser phonons at this higher energy values, which is obvious at a particular temperature. the higher energy states will be less populated as compared to the lower energy states here. Okay, so that's the picture. So now we have, in my lattice, we have electrons and we have phonons. All right, so and electrons, we said you can think of electrons as free electrons. The effective lattice is all incorporated in effective mass, and all the vibrations that are there are all now incorporated in these phonons. Okay, so now it's a question of electrons are there, phonons are there. Do they interact? Okay, do they interact, or they live separate lives here? Before we do that, I took a very simple lattice here consisting of one single atom. Suppose I have a lattice like this here, a diatomic lattice with a bigger mass and a smaller mass like this, bigger mass and a smaller mass like this here. And if we do one is M1 and another one is M2, and if we do again, all that analysis, what we find is, well, we have a mode like this here, where different modes which follow this kind of a relationship. But in addition to that, you will find that there's another solution which goes like this here. You get now two possible solutions. One solution was, I wrote down the equation where omega was k sine ka by 2 here. Now you get another possible solution which is of this kind here. You get two branches. Now you can imagine, as my unit cell becomes more complicated, I will get not only these two, but I'll get more branches. Okay, different branches of omega versus q relationship here. Now this one is what we call as an acoustic branch, and this one we call as a optical branch here. And the reasons for this acoustic is because, as I said, if you take the slope here, what do you get? You get basically the sound velocity. You get the sound velocity in that particular medium here. So whatever crystal is there, you take the slope and it gives you the sound velocity here. So that's where the name acoustic comes here. The name optical comes here for the following reason. Suppose for a moment that this is sodium. I have an ionic crystal. This is sodium and this is chlorine. Now, which one is larger? Chlorine is larger. All right, so let's say this is chlorine and this is sodium. All right, sodium chloride crystal here. Now you get an electromagnetic radiation which is incident on sodium chloride. All right, so before that, what I wanted, before the number, here what you find is the acoustic branch, the bigger ion and the smaller ions are all moving in the same direction. Okay, while in the optical we can show through our solution that they are out of phase. Out of phase means the red one is moving towards the left and the blue one is moving towards the right here. That you can show that this is what is happening in this particular branch here, optical branch. While here they are moving in the same direction here, so we call it coherent movement and we call it out of phase movement. So that comes about from the solution of those simple equations that we have. Now, why am I calling it optical? As I said, imagine that this is chlorine and this is sodium here. So chlorine is negatively charged, sodium is positively charged here. So imagine an electromagnetic wave is incident. What will this electromagnetic wave do? It has an electric field, right? What will this electric field do? What will it do to the chlorine? Let's say it moves it towards the right. What will it do to the sodium? Move it in the opposite direction, right? So if it is of the right wavelength, what is it going to do? It's going to make these atoms start to vibrate. Okay, so the electromagnetic radiation comes in and will start moving this here and makes it vibrate. And as it vibrates, then what is happening? So you've excited vibration. So which means what? It has absorbed radiation. It has absorbed radiation here. So that's the reason why we call this the optical branch here. Typically, these wavelengths may be in the infrared region here, and that's the reason why this particular branch is called optical, because of its interaction with electromagnetic radiation. A light of, let's say, infrared wavelength comes in and excites vibrations here. And what kind of vibration? This one goes right, this one goes left here. And so it excites this particular branch here. And for that reason, it's called the optical here. Now, think about it. This is all a classical picture here. We said that every omega and every q is a mode. And what about the energy in the mode? The energy in the mode is in terms of phonons. So what I can have now, phonons in my system which are called acoustic phonons, and phonon in my system which are called optical phonons. So two kinds of phonons you will find here. Optical phonons and acoustic phonons. All right. Some more complication. If you have lattice here, you can imagine lattice vibrates like this here, laterally, right? What if it vibrates like this here? All of you know that two kinds of waves are there, sound waves, transverse, longitudinal. So you can get all of that. So I can have a branch which is like transverse acoustic. I can have a branch which is longitudinal acoustic. So I can have all these transverse and acoustic, transverse and longitudinal. So now, if I show you, look at the in a silicon, look at the different phonons which are there. There's something called transverse acoustic, longitudinal acoustic, and then we have longitudinal optical and transverse optical. Okay, we have two branches here, and this is showing you for a particular phonon wave vector in 100 direction. Now I will have different kind of a graph maybe in 110 or 111 because the lattice is complicated here. Look at the typical energies of the phonons. Typical energy of the phonon, that acoustic phonons are low energy, 20 milli electron volts or so at the highest point here, and then it reduces and then it goes here. While optical phonons, note that optical phonon energy is all high. Minimum that we see here is 50. Otherwise is higher, 50 and longitudinal, all these energies are on the higher side here. So optical phonons are higher energy phonons. Acoustic phonons they are available at lower energy and available at moderate energies also. Okay, acoustic phonons are here. So normally, if I look at room temperature, what will I find? Will I find optical phonons present in my system? Because the energies are 60 milli electron volts. So you will find there are not many optical phonons present in my lattice. While I will find a lot of acoustic phonons present in my lattice here. So when my electron is there and is moving, and electron, so it's going to interact with these acoustic phonons here. Okay, a lot more. All right, so let's look at then the electron phonon scattering. So I have electrons in my system, and I have these different kinds of phonons which are there: transverse acoustic, longitudinal acoustic, transverse optical, longitudinal optical, with different energies, different densities, and depending on an energy, we'll have different amount of phonons present, which obey the Bose-Einstein statistics here. So how does my scattering take place? Well, very simple thing. My electron has a wave vector k. What can this electron do to a phonon? Well, phonon is what? It's a packet of energy. So it can absorb a phonon, or it can emit a phonon also, right? It can absorb or emit a phonon. So phonon carries a certain momentum, which is q. So let's say there's an electron which absorbs a phonon. So it absorbs how much momentum? Q. Remember, h bar k is what? Momentum. And h bar q is also the momentum of the phonon. So what will be the net momentum of the electron? Has to be like this here. So what happened then? Electron had a particular direction, k, particular wave vector. It absorbed a phonon. What became of the momentum? K dash. It got scattered. K became k dash here. It got scattered. So if an electron absorbs a phonon or it emits a phonon, you know that it's going to get scattered. Now the issue is, you may be wondering, how does this happen here? How does it absorb, or how does this interaction between an electron or a phonon occurs? Okay, so let's look at that. Now you can imagine that what is happening is, as these atoms are moving, the lattice spacing is going to change, right? Normal lattice spacing in silicon is around, let's say, 5 angstrom. But then as this moves here and as this moves here, the spacing between the lattice is going to increase or decrease. Okay, it's going to change. Now, what will that do? Well, let me give you an empirical expression for energy gap in silicon. Energy gap in silicon, this is energy gap at 0 temperature. It depends on temperature. Slightly decreases with temperature. At 0 degree, it is 1.169. And at room temperature, it goes as 1.12. All right, so slight decrease is there. But then what I want to point out is this part here. Energy gap depends on pressure. These are things that people have experimentally measured. That if you apply pressure, the energy gap changes. Now, what is pressure doing? If you apply pressure to a lattice, what is it doing? Effectively changing the Lattice constant, right? Is bringing the atoms closer together. That's it. Right? So what are we saying? That if you change the lattice constant, the energy gap changes. So can you see now how my phonon is going to affect my electron? What my phonon is going to do, phonon is what? Phonon is nothing but the vibrations. And these vibrations will affect my lattice constant. And as my lattice constant changes, U is nothing but the deviation of an atom from its equilibrium position, U here. So this change in U, these deviations will affect my conduction band. So, you can think of sort of a strain in my system. Strain is the change in lattice constant. Strain in my system will cause a change in the conduction band, will cause a change in my valence band. Okay. And the relationship between this change in conduction band and the strain is what we call as deformation potential here. Your lattice is getting deformed because of these vibrations. Deformed meaning the lattice constants are changing. So the lattice is getting deformed, and and as a result of this deformation, a change in conduction band occurs here. So you can imagine something like this happening here. As your atoms are getting displaced from the equilibrium position like this, your conduction band is also getting deformed. Your conduction band is getting deformed. So now you can imagine an electron moving with this kind of a deformation in conduction band. And so that is the source of the interaction between, not going into the details, but that's the source of the interaction between an electron and a phonon. A phonon is a vibration, atomic vibration, and it affects your lattice constants. It deforms your lattice here, and the deformation then results in deformation of your conduction band. And therefore, any deformation in the conduction band, it deforms the potential energy here, and therefore it affects your electronic motion, which manifests itself in terms of scattering here. Okay. All right. So okay. So this is so that is how my lattice scattering then is occurring. So we imagine lattice, all these vibrations as phonons, different kinds of phonons which are present. Phonons distort your lattice here, cause a deformation in the lattice, which then causes deformation in the conduction band and the valence band, and results in scattering. So that's the simple picture of what is happening in lattice scattering here. Now you can imagine as you raise the temperature, you have more phonons, and obviously you have more scattering and mobility decreases. Okay. So this is a picture of the electric field dependence of drift velocity here. Okay, so two things you notice. One thing is that drift velocity, the simple model that we had was velocity was increasing with field. All right, so let's focus on the 300 Kelvin here, graph here. So our simple model showed velocity was increasing linearly with field, but we find velocity keeps on, after a while it starts decreasing and eventually it saturates here. Now the issue is, why does it saturate here? It becomes constant. Why does it become constant? Well, we can explain it on the basis of these phonons here. Note that normally what happens is these optical phonons are high energy. So my electron, there are no optical phonons available, so it cannot absorb and get scattered. So this scattering mechanism is not there. But then as you keep on applying more and more field, what happens to electron energy? Electron energy keeps on increasing. Eventually, electron energy reaches a state where there are no optical phonons to absorb. But what can it do? It can emit an optical phonon. Remember, phonon scattering takes place by both absorption and emission. So as you raise the electric field, eventually a stage comes where I have enough energy in my electron so that it can emit an optical phonon. And then all these, these branches become, all these new scattering mechanisms come into picture here. And my, this thing here, velocity tends to start saturating. So that's because of optical phonon scattering at high fields here. All right, so before we leave, let's do this very simple problem here. So what I want you to do is the following. Estimate the electron energy in silicon close to velocity saturation. Velocity saturation means my electron is saturating, velocity is saturating here at this point. If you keep on increasing field, velocity eventually saturates, and the saturation velocity is 10 to the power 5 meter per second. So what I want you to do is calculate how much energy is there on an average when the velocity is saturated. And how do you do that? Well, the energy of your electron will be, one is a normal thermal energy 3 by 2 kT that it has, plus an energy it has gained from the field. A very simple estimate will be half me times Vd square. That's the energy that it gains from the field. What does this total add up to? How energetic is my electron when I've reached this Vd here? 3 by 2 kT. So kT, as all of you know, is 26 milli electron volt. Mass of an electron is 0.26 times m0, and Vd, we are saying drift velocity reaches its saturation value at 10 to the power 5 meter per second. So what is this energy? (46 milli electron volt). All right, why did I make you calculate? Can you see now it has enough energy, my electron has enough energy to start emitting optical phonons. Remember that this is a very crude number, and electron has a distribution. It's not that all electrons have the same energy. It has a distribution, right? So now it begins to interact with my optical phonon branch here. It begins to emit now, is capable of emitting optical phonons, and so it gets scattered. So suddenly scattering increases very rapidly. Once the electron energy starts to become comparable with this, scattering becomes very high. Scattering becomes very high and the velocity saturates. Okay. The moment my electron gains enough energy to emit an optical phonon, it emits it and it gets scattered. It's not able to gain more energy than about 50 or 60 milli electron volt. It's not able to gain that. Okay, so let's stop here.